Hi there, welcome to this Alchemist chemistry video looking at the nucleophilic addition mechanism using cyanide ions. Now, the first thing we're going to look at in this process of looking at the mechanism is the nature of the carbon-oxygen double bond, or carbonyl group, found within this particular aldehyde molecule. Let's get started. So when we look at the carbonyl group, you'll notice it has a double bond. Let's talk about how that forms. So there are two types of bonding taking place between the carbon and oxygen atoms in the carbonyl group. We have a sigma bond, which is a head-on overlap of two atomic orbitals, one from the carbon, one from the oxygen, creating that sigma bond, covalent bond between the two atoms. That's quite a good overlap, creating a lot of electron density between the two nuclei, and therefore it's quite a strong bond. There's a second bond, creating the second bond of the double bond itself, which is known as a pi bond. This is created by the sideways overlap of two p orbitals. This creates a collection of electron density both above and below the plane of the atoms themselves, and is usually a bit more diffuse and less concentrated than the sigma bond in terms of the nature of the overlap and the concentration of electron density between the two nuclei of the carbon and oxygen atoms, and therefore usually it is the case that the pi bond is weaker than the sigma bond. So in this respect, we can say there's a commonality between carbon-carbon double bonds in alkenes and carbonyl groups. They both possess a double bond, and therefore there is a greater concentration of electron density between the two nuclei when there's a double bond when compared to a single bond. But at this point, we're going to differentiate between alkenes and carbonyl groups by talking about the fact that the carbonyl group has polarity, and we'll talk about that now. So the key idea here is that oxygen is a more electronegative atom than carbon. Electronegativity is defined as being the ability or tendency of an atom to pull a pair of electrons towards itself within a covalent bond. So what's happening here is the highly electronegative oxygen is pulling electron density towards itself along this bond, and that's creating a delta negative, or a partial negativity around the oxygen. This means the carbon is being left delta positive or slightly positive, and this makes the carbon susceptible to nucleophilic attack. So the question you ask yourself now is, what on earth is a nucleophile? Well, nucleophiles are usually molecules that contain either a lone pair and a delta negative charge or a full negative charge, and are therefore very good at donating a pair of electrons towards a region of positivity, like a delta positive region of a molecule, for example. And therefore they're defined as being electron pair donators. And the cyanide ion is a very good example of an effective nucleophile. Now that we've fully investigated the nature of the carbonyl group found within this aldehyde, we're going to look at the mechanism itself, starting with the nucleophilic attack of this nucleophile, the cyanide ion, on the delta positive carbon found within the carbonyl group of this aldehyde. Now, the conditions required for this reaction to take place are usually either the presence of sodium cyanide or potassium cyanide in acidic conditions with hydrogen ions. That will generate hydrogen cyanide in situ. We don't generally use large amounts of hydrogen cyanide due to its toxic and dangerous nature. Therefore, we tend to generate small amounts of the substance in situ using these particular reaction conditions. So when looking at the first step in this multi-step mechanism, don't forget that a curly arrow represents the movement of a pair of electrons, and we're going to need to show the polarity of this carbon-oxygen double bond using partial charges, delta positive, delta negatives, to show where this nucleophile is going to attack. And the mechanism would look a bit like this. So what we can see here is that the lone pair of electrons from the nucleophile, the cyanide ion, are being donated towards the delta positive carbon of the aldehyde. Because of the delta positive nature, it's going to be attracting that pair of electrons from the nucleophile towards this delta positive carbon. Simultaneously, the pi bond in the carbon double bond oxygen is being broken due to repulsion. The approaching electrons here are repelling the electrons in this pi bond towards the delta negative electronegative oxygen, causing this pi bond to break. Next, let's look at the aftermath of that process and the interaction of the currently unused hydrogen ion. And that would look something a little bit like this. When the pi bond broke, the pair of electrons were being donated towards that oxygen, which now possesses that pair of electrons. And it now has an overall negative charge as it has a greater electron density associated with the oxygen itself. This will then be attracted towards the positively charged hydrogen ion from the dissociation of hydrogen cyanide into hydrogen ions and cyanide ions. So basically what's happening is this negative oxygen is donating electrons and accepting and forming a bond with this hydrogen ion to form an OH group. And finally, in step 3, our final step, we present the finished product. a hydroxynitrile molecule. And specifically, this is 2-hydroxypropanitrile. Finally, I want to touch on an interesting aspect of this particular mechanism and the nature of how the cyanide ion attacks that delta positive carbon and how it attacks it in terms of its orientation in space and the way it approaches the delta positive carbon, which allows the formation of things like these optical isomers. Due to the planar nature of the carbonyl group itself, the fact that it is flat in the plane of the piece of paper or board we're looking at, there is a 50% chance that the cyanide ion nucleophile can attack from below the plane of the molecule, but equally a 50% chance that the cyanide ion will attack from above the plane of the molecule when it attacks the delta positive carbon. And so that means we're going to produce something known as a racemate, a 50-50 mixture of the two different possible optical isomers that can be produced when this mechanism takes place. And I'm going to talk about those two optical isomers now. So the important feature these two versions of 2-hydroxypropanitrile possess is they have a chiral center. This is a carbon atom which is bonded to 4 different groups around itself. And this creates the opportunity for something known as optical isomerism. Optical isomers are 2 molecules that are non-superimposable mirror images of each other. And therefore, their groups occupy different orientations in space, and they're locked in these configurations. You can see in both the tetrahedral versions of the molecules I've drawn and the molymod kits that the right-hand molecule is a reflection of the left-hand molecule in the mirror plane, creating optical isomers, or otherwise known as enantiomers. And there you have it, guys, a full run through of the nucleophilic addition mechanism using cyanide ions. Please check out the card to look at my next video, which will be looking at the nucleophilic addition mechanism using hydride ions and therefore looking at reduction reactions. Thank you so much for listening. Take care. Bye for now.